Good morning. We begin lecture 14. We will quickly review some of the concepts in lecture 13 and then build on that. So, the flow of today's topics, the last lecture, one of the key results that we have obtained is the noble identities. We will describe that. We will look at an alternate way of describing. We have described the operations of the downsampling and upsampling using the frequency domain. There is a very interesting way of looking at the multi-rate, not the sampling rate conversion, but the multi-rate filtering point of view. So, that is the point that we want to highlight. Then of course, polyphase decomposition, we gave the introduction. We will now show that there are several advantages with the polyphase filtering. And what we will develop towards the end of the lecture is the application of the multi-rate structures for what we refer to as filter banks. Very useful, very powerful concept. It is related quite extensively to communications. So, just to sort of give you a feel for where all do we see filter banks. Whenever you compute an FFT or an IFFT, you are actually doing a filter bank operation. Today in the cellular world, we use OFDM for most of our 4G systems, and looking ahead it looks like it will be part of the 5G systems as well. OFDM is also another flavor of the filter banks that we are going to be studying. Wavelet analysis filter bank. So, basically there is a whole range of applications that come under the umbrella of the filter banks. So, we will look at the first of the filter banks, which we call as the DFT filter banks that use the DFT as the underlying computational tool. So, this is a starting point to understand and apply DFT filter banks. And of course, what is DFT used for? Primarily for spectral analysis. So, we will make a comment about using DFT for spectral analysis as a tool for spectral analysis. Once you see the filter bank relationship, you will probably be able to see the reasons why you would either do DFT and spectral analysis or not do that. So, again these are the insights, and that is precisely the reason for studying a course like this, because it has got its links. It already builds on the framework that you have developed, and importantly it shows you, gives you insights that help you understand the tools that we work with in communications and signal processing. So, that towards the end we will get to that, or probably in the next lecture. Okay, so a lot of very interesting things to discuss today. So, we will move quickly through some of the points that we want to do. So, lecture 13, a recap or a review, of course with a little bit of some new elements, avoiding complete repetition of the things that we have discussed. One of the key results is the ability to interchange the upsampling and the downsampling. Again, I write this multiple times because this is one of the key results that help us in developing efficient multi-rate structures. So, L and M are equivalent to the interchanged order if L and M are prime. Downsampling can come first, followed by the upsampling. Okay. So, this is if and only if L and M are relatively prime. Relatively prime is enough, they do not have to be prime numbers themselves. Okay. So, an application or an example for this, let us quickly look at it. So, I have z power minus 2. I have downsampling by a factor of 2, upsampling by a factor of 3. Of course, I can interchange these two if I want to, because they are relatively prime. Now, the problem itself at this point is not the, I think, the fact that you can interchange, but keep this example with you, we will come back to it in a minute. So, the noble identities, and then we will come back to this example. Noble identities tell us that if you have a filter of the form h of z power m followed by a downsampling, this is typically the structure that you would have for anti-aliasing filtering. So, this is the structure for anti-aliasing filtering. Okay, this is the structure for that. this combination. So, anti-aliasing filtering followed by the downsampling, and this would be a correct way or the more efficient way of doing this will be to do the downsampling first followed by the filtering. H of Z now, it is no longer H of Z, Z power m, it is not just an interchange of the two, these are time varying systems. So, therefore, we cannot just interchange them. So, the key point, that is one of the identities, and of course, the second one addresses the structure that we will have for interpolation. Interpolation says you do the upsampling followed by filtering, and if you have a filter of the form H of Z power L, then the noble identities tell us that you can do the filtering first, again it is H of Z followed by the upsampling factor, and we have shown this both through the transform domain as well as the time domain. We have looked at it and demonstrated. So, this is the structure that we get for interpolation after you do the upsampling interpolation. Okay. Now, notice I did not say this is anti-aliasing filtering, or this is only the structure or the form or the sequence in which the filtering and the multirate structure. Why do I specifically say that this is just the structure, not actually anti-aliasing filtering? Because of the following: H of Z power m cannot be a low pass filter. And why is that? It will have multiple copies of the spectral. So, can it be a high pass filter? So, low pass filter is not possible. Can it be a high pass filter? No. Okay. What it can be, what it has to be is a multi-band band pass filter. Okay. So, definitely that is not what we need for either anti-aliasing or for interpolation. So, therefore, this is only the form of the noble identities. Okay. Now, please apply the noble identities and simplify this. So, this is equivalent to, let me use the red at the first stage, I can interchange the, so the delay and the downsampling can be swapped. If you swap it, then you will get the delay for downsampling followed by Z inverse followed by upsampling by a factor of 3. Can you shift the filtering the delay to the right of this? I want task is to do that. So, this gives me, if I want to have the Z inverse followed by the upsampling, and I want to move the delay to the right of the upsampling, it will become downsampling by a factor of 2, upsampling by a factor of 3, and this becomes Z power minus 3. Again, these multirate structures do give us certain results or tools which may not be very obvious unless you actually sit down and write it. But if you are able to keep the multirate identities in mind, then it is easy for you to do these changes. Okay. So, we will come back to looking at several of these type of applications, because multirate is all about developing tools of this type. Now, I would like to introduce to you the description, time domain description of multirate filters, time domain description of multirate filtering. Okay. So, the two forms of multirate filtering that we encounter very often are the anti-aliasing filtering and the interpolation filtering, and we will write down expressions for both of those. So, the first one that we look at is the anti-aliasing filtering. I have H of Z if my input is x of n followed by the downsampling by a factor of m, and I write down the output. I call this as y1 of n, have one intermediate signal which is helpful for me to get an expression for, let me call that as x1 of n. Between x and x1, it is an LTI system because it is a digital filter. So, I can write down the input output relationship between x1 of n and x2 of n as a convolution, k equal to minus infinity to infinity x of k h of n minus k. Okay. So, input output relationship, LTI system, first stage. The input as x of n, output as y1 is not an LTI system. So, therefore, in general difficult for me to write that relationship. However, we do have the following: y1 of n is x1 of Mn, that is the downsampler. So, nothing prevents me from substituting 2 in 1. If this is equation number 1, this is equation 2, I can substitute 2 in 1 and actually get a input output relationship that looks like convolution, but it is not, because it is not the sliding convolution. It is a operation that it is a operation that is similar to convolution, but it is different in terms of the indexing. So, this would be k equal to minus infinity to infinity x of k h of Mn minus k. This would be y1 of n. So, in other words, you do not take all the the entire impulse response, you take some shifts of the impulse response, not all of them, and therefore, that is like saying, okay, some shifts, when you think of it in terms of the convolution, I do not need all the shifts, but at any given shift you will take all the inputs for doing the computation. So, this is, you can find interesting ways of interpreting this result. I will leave that as a exercise, or something that you can write down as an additional note to this one. Okay. The second, we have the second operation is when I have the upsampling by a factor of L, followed by the interpolation filter h of z, and if you call this as x of n, this as y2 of n, and the intermediate signal, let me call that as x2 of n. You need to be a little bit careful with the interpolation, but it turns out that there is a very simple way of writing the expression for this as well. So, the input output relationship where the LTI part is concerned is easy for us to write down. Y2 of n is summation k equal to minus infinity to infinity x2 of k h of n minus k. Okay. Now, write down the input output relationship for the upsampler. X2 of n is equal to x of n by L. You probably are very familiar with this by now. If n is equal to a multiple of L equal to 0 otherwise, now let me just impose this condition on the previous equation. So, basically what it says is that there are lots of 0 valued samples in x2 of n. So, basically this summation can be rewritten as y2 of n instead of course k will go from minus infinity to infinity, but the only things that are of interest or of actual computation will be when k equal to a multiple of L. So, if you impose the additional constraint multiple of L, you do not change anything, because you are only looking at those values of x2 that are non-zero. So, this would be x2 of k h of n minus k, and whenever you have such a constraint, it is basically it is of the form k is equal to m times L. K goes from minus infinity to infinity, that means m goes from minus infinity to infinity. So, this will be summation m equal to minus infinity to infinity x2 of m L, wherever there is k, I am replacing it with ml, h of n minus ml, h of n minus ml. So, of course, x2 of ml is nothing but x of m. So, this can be written as summation m equal to minus infinity to infinity x of m h of n minus ml. What this says is the input output relationship, all the samples of x are involved, but in terms of the filters, I use not all the impulse response coefficients. For a particular shift, I use a subset, a grid of the impulse response. Again, that is another way of visualizing what happens when you have a lot of 0 valued samples. The filtering actually looks like you are applying some kind of a grid onto your data system. Okay, so this is another result that you can note down. So, this is equal to y2 of n. Now, the third of these, which is also a useful and interesting result, is when I do a fractional sampling rate change. Upsample by a factor of L, filter by h of z, it will be an ideal low pass filter with a cutoff which is minimum of L and M, So I am not writing down all those things, please fill in those details. Down sampling by a factor of m. So, two intermediate signals, there is x1 of n, there is x2 of n, and output is y of n, input x of n. I would like to relate the input and the output in the following way. So, y of n is x2 of mn. x2 of n, we just now did the upsampling, explanation for the upsampling. So, I will just use the expression from the last derived result. So, x2 of n can be written as summation m equal to minus infinity to infinity x of m h of n minus ml, am I right? That is the last expression that we have just written down for the upsampler. So, combining equations 1 and 2, we get the final result, which says y of n also has got a very nice compact expression m equal to minus infinity to infinity. This is x of mn, wherever there is n, replace it with mn. So, this would be x of m, no change, it does not have the the variable n. H of, there is n here, I write as mn minus ml, and this is the final result. Interesting to visualize what exactly this equation is telling us. It does throw away some samples, I mean it will, so it does not compute all samples, but it has a very interesting structure in terms of how the filtering is done, which samples are retained, which samples are discarded. Okay. So, think about it, it is not difficult once you spend a little bit of time. Again, it is an interesting way of looking at it, more for insight.